Okay, we're going to do a review of Category 4, but as it says, I'm not really going to do Category 4. We are really going to look at Category 5. The reason I'm not looking at Category 4 is here are the standards for Category 4 conic sections. So my advice on this is come to class, do your work, make sure you get this down, because this is what we're covering in class right now, and you will have this fresh on your minds going into your test. So I'm going to focus on the rest of the categories. So Category 5 is properties of square root functions. So we're going to begin with supporting standards and work up to the one and only readiness standard in this category. I believe we have 5 questions coming out of this category. So beginning with, know your parent function. Your parent function looks like this. F of x is equal to the square root of x. This is also called your radical function, not to be confused with rational. So you have to be able to investigate, describe, and predict the effects of parameter changes on the graphs of the square root functions. Describe limitations on domains and ranges. So we're going to go through information here. So I have a graph. I have a verbal description right here. And the rest of it I'm going to fill in. So this is going to help me the most. Vertical translation up to. So from that, I can actually go ahead and write my equation based on what I know about AH and K. So if there is no stretch or compression, then my A value is still going to be 1, as it is in its parent function. Square root of x. Vertical translation up to means K has changed, and K goes outside of the square root. So this is the function right here. I can graph that. My vertex point will be located right here. And that is HK, which is 0, 2. And from that, I can also get my domain and my range. So the domain is beginning at H, so it's going to be the set of all x's, and I don't have room to write out the correct notation, so pretend the set of all x's greater than or equal to 0. The set of all y's greater than or equal to k, which is 2. And then I can also fill in points on my table by graphing. So when x is 0, y is 2, and then the rest are decimal values. So I would graph that and bring up my table to get the rest of these. So I've given a few blanks here for you to fill in if you just want to pause and see if you can write out an equation and then graph it and make it match up with your table, make it match up with your graph on these. And in doing so, you have also reviewed supporting standard 2A.9b, which says relate representations of square root functions in their algebraic or equation, tabular or table, graphical, graphs, and verbal descriptions. So what we just did on that previous page, you have your algebraic right here, tabular, graphical, verbal descriptions. So that's what that means. So moving right along. 2A.9d says determine solutions of square root equations using graphs, tables, and algebraic methods. So first of all, because this is a timed test, when you are just asked to solve a square root equation like the one shown here, you're going to go to your graphs because that is the quickest method. It also eliminates any extraneous solutions. So in other words, when I'm doing this algebraically, I might get a solution that when I check it doesn't work. So it eliminates any of that, and it's just a whole lot faster. So I've got some screenshots here of solving using graphs, and so this is how we've done it all year. To solve using graphs, I'm going to split this up right at the equal sign, and I'm going to graph the left side. So I have my 5 plus square root of x minus 3. Those parentheses are not necessary. And I have 9 graphed. And then I have zoomed my window out to find my intersection point and I want to know what x is. So my solution is not this whole point. My solution is x equals 19. And that's what we're looking for here. So that's using our graphs. Using the tables, I'm looking for, and so I went ahead and hit Control T. I brought up my table, and I'm comparing my f1 of x to my f2 of x, and where those are the same, that's where my solution is. So this shows again that my solution is at x equals 19 on my table. And we'll go ahead and solve graphically as well. So if I want to solve this graphically, I'm going to isolate my radicals. That means that this 5 is moving to the other side. So that's going to leave me with square root of x minus 3 is equal to 9 minus 5, which is going to be 4. And then I need to undo my square root, so I am going to square both sides. And so that's going to give me x minus 3 is equal to 16. And then I'm going to add 3 to both sides, and x is equal to 19. Now solving algebraically, you have to take the time and go back and substitute then in and make sure that that works, because you do have the chance that it's extraneous. So 19 minus 3 would give me 16. The square root of 16 is 4. 5 plus 4 is 9, so my answer checks out here. Pulled some questions from released questions, EOC questions from last year, related to square roots and solving. And so given this equation, the square root of x over y is equal to 4, what would represent y in terms of x? So basically what we mean is solve for y here. So if I have this as my equation to start with, then I'm going to go ahead and square both sides. So I get x over y is equal to 16. And then probably the easiest thing to do here would be to turn this into a proportion. And so I get 16y is equal to 1x. So y is equal to x over 16, which will be answer choice C. This was also released from EOC on last year's test. What value of p is a solution to the equation below? Of course, we have calculators that have nsolve, so nsolve is an option here, not necessarily recommended, because we always have that chance that there are multiple solutions and we're only going to hit the first solution and miss the one that matters to us or something. Probably wouldn't have that problem here. We're going to go ahead and do this algebraically. So I'll write it out here so we have some room to work. So again, I'm going to isolate my radical. So I'm going to move my 1 over. So plus 1 is 4. And I'm going to divide by 8. So I have the square root of p is equal to 4 over 8, which reduces down to 1 over 2. Then I'm going to square both sides. So I get that p is equal to 1/2 squared, which is 1/4. And then since this is going to be bubbled in, I'm going to assume that it has to be in its decimal form, which is going to be a 0.25. There's your answer there. This was also from EOC, so I pulled this on here, and we're going to look at another problem related to pendulums in a minute. This seems to be a favorite. So we have a formula, p, or the period of a pendulum, is equal to 2 pi times the square root of the length of the pendulum over 32. And so the only thing that changes in this equation is your L and P and how it's used. So here's my equation. Pendulum's period in this point is 1.6 seconds. Which of the following is closest to the length of the pendulum? So we're going to identify, first of all, since we're using our graphs to help with this, what P represents and what L represents. So if I'm graphing, then what I have is y equals 2 pi times the square root of x over 32. So y is my period of the pendulum, and x is the length of the pendulum. So that will help me when I actually get my intersection point, which I've done over here. That will tell me which part of that point I'm looking at. So they told me that the P was 1.6. So what I did is I went ahead and set up an equation that looks like this. So I set 1.6, or P, is equal to 2 pi, and then everything else is going to stay the same. Square root of x over 32. And then I graphed my left side. Here's my 1.6. I graphed my right side, and I had to zoom out a little bit here, and I found my intersection point. Intersection is at 2.8, 1.6. And so what I've done right here helps me know which to use for my answer, because notice there are two possible answers here if you're not careful. So this one right here is close to my y value, this one right here is close to my x value, but it asks specifically what is the length of the pendulum, so I'm looking for the x value right here. So the answer choice closest to that is 2.1. Okay, supporting standard 9C. Determine reasonable, there's our big word, domain and range values of square root functions, and then interpret and determine reasonableness of solutions to square root equations and inequalities. So it's not enough to just be able to solve, you have to be able to prove it or justify it and show that it's reasonable. So I pulled this in right here because the equation I'm using is really similar to the one, well, almost exact, the one we just used. The only change in this is that instead of pendulum period, I'm using t for time, and instead of length, I'm using a height. So here is our situation. We're at an amusement park, and there's a ride called the pirate ship. And so people are looking, they're sitting in this huge ship that's swinging back and forth, kind of like a pendulum does. And Thalia, for some reason, is measuring how long it takes for the ship to move all the way from one side to the other back again. So she says it takes between 7 and 8 seconds for the ride to make a complete swing back and forth. And so the question here is possible domain values for this ride if one complete swing is between 7 and 8 seconds. So we're talking about what's reasonable for the situation. So first of all, in general, for square roots, if I just graphed the equation I'm given right here, my h and k are at 0, 0, and so in general I would say that the domain is going to be the set of all x's, where x is all real numbers greater than or equal to 0. And my range would be the set of all y values, real numbers greater than or equal to 0. So in general, that would be the domain and range. But that isn't reasonable for my situation, because that is saying that this will continue to go up forever, my height here, and that my time will continue to go on forever, and we know that the ride will stop, so that's not reasonable. So what we're going to do then is find values. So they said that the time was in between 7 and 8. So again, being very careful here, because generally time is on our x-axis, but in this situation it's not. T, time, is our y value, height is our x value. So if I want to know when it's between 7 and 8 seconds, I have to scroll down in my y values here and pick up between 7 and 8 seconds. So looking at my table, I can kind of estimate that it's a little less than 40 in height and a little less than 52 here. I can find the exact values by using nsolve, and so if I set 7 seconds as my time and just put that into my equation, I find that the height at 7 seconds was 39.7179. At 8 seconds it was 51.8764. So I can't give exact domain and range for this situation. I know that my domain, which is the height, at the very most would be 51.8764. So beginning from 0 we're assuming that it's like on the ground because they don't give us that information, though I'm sure it is actually raised off the ground. But from the beginning point, whatever that is, up to a maximum height, very highest it could have been based on our data right here, would be 51.8764. But it could be less than that. It could be somewhere in between because we know it's between 7 and 8 seconds. But that's an estimate. And then our seconds right here, we do know that they begin with 0 seconds when we begin the ride. And at the longest it went for, again we're talking about just one swing back and forth, is all we're looking at right here, would be from 0 to a maximum of 8. So we don't know exactly what it is. But that is much more reasonable than what we were looking at before, just saying that it goes on forever in either place. Point 9G, connecting inverse of square root functions with quadratic functions. This has some restrictions in domain and range as well. So I'm going to work both directions. I'm going to start with quadratic and go to its inverse, which would be a radical. And I'm going to start with my radical, my roots, and find its inverse, which would be a quadratic. But we will limit, we'll have to put a limitation on domains here, because remember, quadratic looks like this, whereas square root is just this part of it, so we have to restrict and only use this part of our quadratic function in order to get the inverse for this. So the steps we use here, f of x is the same as y, so the first thing we're going to do is swap x and y. So I'm going to say x equals 2y squared minus 2. So x plus 2 is equal to 2y squared. So x plus 2 over 2 is equal to y squared. Then I need to take the square root of both sides. So what I get here is that my inverse, I'm going to use the inverse notation that you'll probably see, f negative 1 of x, is everything under the radical in this situation. X plus 2 over 2, or that could be 1/2 x plus 1, if you wrote it that way. But we're going to restrict it, so my hk here was at 0, negative 2. And so this one I'm going to break, so that's going to be everything for only values greater than or equal to 0. And I'm talking about my quadratic specifically here. Same thing right here, so I'm going to say x equals square root of y minus 3 squared plus 1. So x minus 1 is equal to y minus 3 squared. So I already have my power isolated, so I'm going to take the square root of both sides, which gives me the square root of x minus 1 equal to y minus 3. And I'm going to move that 3 over, and when I do so, it is not under the root. So what I wind up with is the inverse function is, I'm going to have room here to write this. Sorry, I'm going to come down below. Square root of x minus 1 under the root plus 3 outside the root. And I can graph and check that. And my hk values here are 3 and 1. So this was my vertex for this function. So this is where I want to start my domain. So I'm going to restrict it to values greater than or equal to 3. So in other words, when I graph that, quadratic, here's my vertex point, and I'm saying only use this side of my parabola, because this side over here wouldn't produce a function if I did that, so I've restricted this. And then we're going to work the other direction. So So this time I have radical and I'm going to work back towards the quadratic. So I have x equals 2y plus 8. So I'm going to square both sides. So I have x squared, and when I do that, my square root is eliminated, so 2y plus 8. Then x squared minus 8 equals 2y. And so my inverse will be x squared minus 8 over 2. Or, go ahead and write that in its kind of an AHK form. It will be 1/2 x squared minus 4. So then my vertex here is at 0, -4. So I would want to set my domain as values greater than or equal to 0 on that. Same thing here. I have x equals square root of y plus 3 minus 1. So x plus 1 equals square root of y plus 3. Square both sides, so that's going to be x plus 1 in parentheses squared, if the whole quantity squared, is equal to y plus 3. So my inverse, again, I'm going to run out of room here, too much on one page, is the quantity x plus 1 squared minus 3. And so my HK value here is -1, -3. So I'm going to restrict this for values greater than or equal to -1 to use only that half portion of my parabola. Alright, and then finally the readiness standard. This is where the majority of your questions are coming from. So if we have 5 questions coming from this category, 60 to 65% of that is going to be readiness standards. So you can figure about 3 out of those 5 at least are readiness. But here's the thing, I mean, look at what we have here. Analyze situations modeled by square root functions. Didn't we just do that? Formulate equations, that's the only thing I see here that's kind of new. Select a method for solving, we did that. And solve problems. And somewhere in all of this, my page for inequalities got lost. So I'll go back in a second and let's just talk about how to solve inequalities as well. But the only thing on here that I can see that we haven't specifically looked at is formulating equations. And so let's look at this situation here. I'm not really sure how to predict how this is going to show up. But here's our situation. We took a balloon ride and we're given this data from our balloon ride. So the height in meters and the distance in kilometers. And so this table is going to be set up horizontally, but the same way as we normally would. The column you see first is x, the column you see second is y. So your height is your x values, your distance are your y values. And so I've done some calculations over here already. So if I'm trying to write an equation, then I'm using y is equal to a times the square root of x minus h plus k. And we know that if you're getting on a balloon ride, you start at 0 meters and you start at 0 kilometers. So your h and k are both 0 here. So all we really need to find is a in this situation. So I'm going to substitute in the variables that they're using. So the distance is equal to a times the height, just so that I get things in the right places. And so if I want to find a, then I'm just going to take some points and substitute in. And so that's what I've shown right here. So I took the distance, 3.833, and I substituted in here. and I took the height that goes with that and substituted in here, and I found an A value, 3.57167. And just to make sure, I took one further along to verify, and I substituted in it again, my distance and my height, and I came out with the same A value. And even if it's a little bit off, which is possible in your data because you're kind of estimating, it's going to be close enough to tell. So my equation for this would look like, so I just substitute in what I found, 3.5716 square root of h. And then I could use my x and y and go ahead and graph that, and I can pull up other values here and then make predictions based on that information. So that's just quickly how to find A here. So let's talk inequalities for a second. So, pretty sure I had a whole page done on this and I lost it. So let's say, well, we wouldn't want equal sign for inequalities, would we? Let's go ahead and just use y. I don't like using the y here because I know that the test is going to have so much of the f of x on it, so I don't want us to get too... Okay, let's do it this way. So let's just say we have an inequality, let's say the square root of 5x plus 3 is greater than or equal to 9. Right, so the fastest way to solve this is going to be graph this side, find your intersection point, and so on the number line we can mark our intersection point, and there should only be one for a square root. And then at your intersection point, that will be a solid circle because it's greater than or equal to, closed circle. And so then choose a test point here, find which one is true, and shade. So if this area was true, then you would say it's greater than or equal to your test point. If this area were true, it's going to be less than or equal to, to your intersection point, not your test point. Algebraically, we solve it the same way as we would any other problem. So we're going to square both sides. So we get 5x plus 3 is greater than or equal to 81. So 5x is greater than or equal to 81 minus 3, which should be 78. So x is greater than or equal to 78 over 5. And then you can reduce that or turn it into a decimal or whatever. If you're doing it algebraically, again, you have to plug it back in here, substitute in, and check it because it could be extraneous solution. So this is your foolproof method, and it's also your faster method for the most part in solving. And that about covers category 5. And like I said, we're looking at category 4 in class. Now I posted several pages to go along with this in Edmodo, so there's some practice on finding domain, practice on solving square roots, practice on solving inequalities. Maybe that's what I did with it. I knew I had a page somewhere. There's a page saved there and posted for you. And I think that's all.